Hello everyone, and welcome to class for week number 2 of our falling mass rotating pulley experiment. There are two things I would like to discuss today. So first of all, I want to say a few things about how we're going to be able to measure the acceleration in our system. The other thing I want to talk a little bit about is the measurement circuit, namely how this is going to be a little bit different from what you've been using all semester, and the major way in which it's different, there's now going to be a computer interface that helps us take data much more rapidly than we could have by hand. So just to recap from what we talked about last time, right? So last week in class and in lab we developed theoretical models for what's going on, and in particular for the acceleration of our falling mass as it unwinds. Now I've drawn here the acceleration as a vector indicating its direction. The quantity we predicted last time was the magnitude of that acceleration, and I'm going to follow the manual's notation here and just write plain A to denote the magnitude of the vector acceleration A vector. Now we were able to predict what this acceleration should be in magnitude, but the question is, how do we measure it? Well, you might have some thoughts about how to measure accelerations because you've already done that, right? So in the linearly accelerated motion experiment, you were able to use use your timers to measure how fast the cart was going, and from that you were able to infer the acceleration. So in lab, you use this idea that v final squared equals v initial squared plus 2a delta x, right? And what you were able to do was measure, right, so we assumed that this was 0. We measured v final with photogate, right? You also measured the displacement of the cart, right? With a ruler, and by plotting a graph of v squared versus the displacement of the cart, you were able to infer the acceleration. And now you know how that velocity measurement worked, right? So you had a paper card that you taped to your cart, and then as the cart slid past your photogate, it blocked light, and you were able to measure how long the light was blocked. Now, we could imagine trying this strategy for our falling mass. We could imagine maybe attaching a card to our hanging mass and trying to, get release it from different initial heights and see how fast it's going as a function of sort of different points of release, and maybe we could measure the acceleration that way. But that's a little tricky, right? Because as you thought about last time, we want to be working in a regime where air resistance doesn't matter. And if we're trying to tape a card onto this hanging mass where that mass we know is not going to travel necessarily in like a nice smooth way, like the cart, the hanging mass might be like rotating a little bit as it falls, such that we might actually have to worry about any extra air resistance from the card if we were to do that. And moreover, you'll probably remember that doing this was a little bit tedious in the LAM experiment, right? You had to set it up every single time. You would get, it would take several runs of data just to get one value of the acceleration. So we want to be able to do better than that, right? So instead, what we're going to do here is the following. So what we will do here is the following. We will use our photo gauge to measure not the motion of the hanging mass, but the rotational motion of our pulley. To measure this marker might be fading a little. Pulley. I'll stop using this. So we'll use our photo gauge to measure the angular acceleration of our pulley. As we talked about last time, right, there's a no slip constraint associated with assuming that the string unwinds from this pulley without slipping. Right, so this is angular acceleration. And then what we'll do is we'll use the no slip constraint and that gives the following, that the magnitude of the mass's acceleration is related to the magnitude of the angular acceleration via A equals alpha times r, where r is the radius of our pulley. Okay. So we've changed our problem of measuring linear acceleration into one of measuring angular acceleration. But now the question is, how on earth are we going to measure alpha? Let me erase the board and then I'll tell you how we can do it. So we're going to be able to measure the angular acceleration of our pulley in the following way. What's critical for this is the following, that our pulleys are special and are designed with 3 holes in the pulley wheel, with those 3 holes located symmetrically, that is, forming the vertices of an equilateral triangle. Kind of like what I've drawn over here. So we know how our photo gate works, right? So the way we've designed the photo gate circuit, right? The output of the circuit, before it goes to any other element, right? It's the output is high when light is lost, right? PD and we use this idea in a couple of in like the pendulum experiment and also in the linearly accelerated motion experiment. We're going to be able to make use of the same thing here, right? So let's just sort of think loosely about it first and then we'll be careful, right? So suppose that I set up my photo gate like this, and let's pretend that my pencil here is the light beam. So if I have this shining right through a hole, right, you can see that light can make it through the hole with the pulley wheel in this position, so the signal will be low. But if the pulley rotates, right, now my pencil can't make it through, my light is blocked, we're going to get high. Eventually the wheel is going to rotate enough so that I get to the next hole, and light will make it through again. And so perhaps there's something we can do with measuring how long the light is blocked, which if we know, right, what the angle between these holes is, we can figure something out. When we do know that, we can determine how far the wheel has had to rotate. So let's be specific. So the general strategy use to measure the time that light is blocked by solid part of the pulley, right? And then just like we did for the linearly accelerated motion experiment, right? Then we can find, so let me call this time delta t. Oops, that should be a delta here, delta, right? Then the angular velocity is going to be given by none other than delta theta divided by delta t, where, right, this we can measure with our counter, and this is the angle between poles. Okay. Now, we're going to have to be a little bit more careful about this, and I'll say how in a second. But once we know omega, right, we can do something that's quite similar to what we did in the linearly accelerated motion experiment. So as you probably saw in 117, for sort of every result in linear kinematics, there is an analogous result in rotational kinematics. So just like we use the v final squared equals v initial squared plus 2a delta x, there is a similar result we can use for rotational motion. So use kinematics, and namely, right, so we have omega final squared equals omega initial squared, right, plus 2 alpha delta theta. So this, right, tells me something interesting, right? So if I know, right, I already have indicated, right, how I might be able to measure omega. So assuming I get the details right, so I can measure this, right? If I can also try to figure out how to measure delta theta. So right, delta theta here is the angle rotated through total rotated through after release. If I can measure that as well, right? And then if I can do some graphing, so if I graph this omega final squared versus delta theta, we have a linear model, right? This is my intercept, and my slope here is twice the angular acceleration. So let me box that. So yeah, so graph omega final squared versus delta theta, the slope gives you twice the angular acceleration. Now in order for this scheme to work, we just need to be able to measure omega carefully, and let me now turn to that question. So, let's now think carefully about how we might measure the angular velocity of our pulley wheel. So I'm going to try to do this by drawing some pictures and talking to you. So let's consider a situation where, let's say we initially start off in a situation where, again, here's my pretend photo gate, and we start with the pulley like this. So lights shining right through our bottom hole. Right? Now, if light's shining through the hole, then we know that the beam isn't blocked, and we know that the photo gate signals. Let me draw that here. So let me draw the wheel. So let me attempt to draw this. So I'm going to assume that the photo gate is looking right at the bottom. I got kind of a smiley face there. And right now the photo gate signal is low. So what happens now, right? So if we had it set up like this, right? Our light was coming through. But let's suppose that we had the string wrapped around this, and then this began to rotate. If we rotate this a little bit, and so let me just draw a red dot here to indicate sort of light is making it through, right? So let's try to draw this rotated a bit. Let's see how badly I can do this, something like that. Okay. And then our light is sort of blocked right here. So right at this point, right, with light blocked, our photo gate signal is going to go high. Right? Right, and then this will remain blocked while this wheel continues to rotate, right? At least all the way until, right, we just reach the edge of the next hole. So let me draw that a little bit further for you, right? So if I first try to draw a circle that's round. Okay, so now we'll draw this hole right here, right, and then here's our next hole, and then as this thing continues to rotate, so we're assuming, in case it's not clear, that this wheel is rotating clockwise, right, and then as soon as this rotates a little bit further, we're back in this situation. Right. So let me just move this just a tad over, back. In this situation where light is making it through, and then our photo gate signal goes low again. Right? So I think what you can see here is that, again, depending on exactly where the beam is breaking, is being blocked by the edge of this sort of middle section, and again, it's going to depend on like how well we align the photo gate and like what the thresholds for the Schmidt trigger are. But roughly speaking, right, you can kind of see that that one block is roughly the angle between like the right edge of this hole and then the left edge of the next hole. So like right there. Now, there's a problem with this, right? Because if we just try to do this, because we don't know exactly where the beam is getting broken, so we can measure time PG is high, but, right, we don't know, but angle not well defined. it's hard to tell exactly what angle this rotates through. I think you can see just from looking at this that this isn't like, it's definitely not like a third of a full rotation. If we just look at our pulley, let me just maybe let me bring this like up close so that you can see it better. I wonder if let's see if there you go. Okay, so yeah, I think you can. Whoa, I'm watching on a monitor. Okay, yeah, okay, so you can kind of see right this right here where my finger is not 1/3 of a rotation. So instead, what we're going to do is the following. So let me try to continue this a little bit, right? So I'm running out of room, but I think I can kind of cram this in, right? Right. So if this continues to rotate, right? So over here, we're in a situation where light's completely blocked, right? But then, if this continues rotating to the right, eventually we get to this state over here, where we've rotated to the next, we've rotated to the, whoops, sorry, that should not be, I drew that incorrectly. We've rotated over here, and then we've rotated over here, and our light is blocked. Yep, so here, right, and then, right, so let me just, here, and our light is blocked again. Sorry, my bad there. So you might notice one thing. So when I drew the pulley position, right, notice that the pulley position, like right here, where we had this first initial block, is the same as the pulley position right here when we get this other block again. In both cases, right, the beam, the signal from the photogate goes high just as soon as like this middle section of my pulley starts blocking the beam, right? Now we're on to something, right? Because this is well defined, right? This is exactly 1/3 of a rotation. And specifically, right, you know that a full rotation is equal to 2 pi radians, right? And so 1/3 of that is 2 pi over 3 radians. Okay. So if we want to know, right, how, we want to essentially time how long it's taken to rotate through 1/3 of a radian, right? What we actually want to measure, and again, let me just for clarity shift this over just a little bit. Right. What we actually want to measure is this time interval here. We want to measure that. Let me let you take a moment to think about what might be a useful circuit element that we've talked about before that could do this, namely measure between this rising edge and the next rising edge. So welcome back. Hopefully you had a chance to think about this, and maybe you're thinking, well, if I want to measure the time between 2 rising edges, I could just use a divide by 2 circuit. So if I do that, right, so if I do PG divided by 2, right, then I'm going to get the following, right? If I assume we set this initially low, right, then it's going to go high at the first rising edge, but then not do anything else until we go to the next rising edge, at which point it drops. So if we now take this photogate divided by 2 and then AND it with our reference clock, just as we've been doing before, now we have the ability to measure what happens when the pulley, how long it takes for the pulley to go through 1/3 of a rotation. What I'm going, I think, to do now is to cut to my computer where I can show you the detailed timing diagram of this in a little bit neater than I can draw on the small board here. And then I'll tell you about how the whole thing, how the circuit and the timing diagram work.